And we're back into the fascinating world of NATEX continuous integration, or NATEX CI. In the last video, we said that we are now testing this build and retry mechanism, meaning if we build a target for NATEX CI and it fails, we will retry the build up to 5 times. This has been implemented. We are now testing it very slowly. We are testing it in the NATEX main repo, as well as a NATEX mirror repo and our NATEX build farm. This logic here is meant to fix our problem of failed downloading of dependencies. But the downloading of dependencies, the failure, doesn't happen that often. So that's why we're taking our time to test it. It happens quite rarely at certain periods. We're not sure what the pattern is. It seems to be happening more often sometimes. Right now in this period, it's taking a long time to reproduce, so we are waiting for it to happen and to check our logic, which may take a few weeks. What do we do in the meantime? Well, we go back to look at other reasons for our high utilization of GitHub runners. Remember back in January and February 2026, we have a situation with our GitHub runners. We are running too many jobs. We are spiking our GitHub runners way beyond the recommended average of 25. Therefore, we need to understand what happened here. To do that, we looked at the most expensive PR. We ran a job to export all the GitHub jobs and all the PRs, match them together, and we compiled a list of the most expensive PRs. In one of our earlier videos, we were investigating the reasons for this PR. Why did it take so long to build? And we looked at the first couple of failures. For example, we saw that this failure was due to downloading errors in the DTC device tree and also the OpenAMP library. Then we went into the next failure and we saw that it failed to download the microADB library. Yes, so far we have lots of download failures. Even though there are 2 libraries here, the downloading failed 4 times. The downloading failed once here. Therefore, if our retry logic works, it will fix this problem. It will retry and re-download these libraries, and we should not encounter these errors anymore. We also saw one compile error. This could have been fixed by compiling our PRs in our local repos before submitting to NATEX main repo. I will talk a bit more about that in a while. Then we have a compile error with this specific target, BL602 EVB:ELF. This target is a RISC-V target. It's known to have erratic build errors. Sometimes it will just fail to build. So what we've done is that we have disabled this thing altogether. This target will never ever be built by NATEX. Therefore, we should not see this error again in the future. We have done the assessment of the earlier failures. We have not. So today we'll go through the rest. We haven't done the rest of the failures in the last session. Today we'll see what else contributed to this PR taking so much time to build in NATEX. Now, as we go down the list, we see another error here, failure. This is due to MCU boot, which I think we also covered in the last video. Unfortunately, we have 2 build failures here. When we click on it to see it, what happens was that the lock has expired. So we have no idea why it failed. And that's how we are doing this video today. We are going through and clicking through the logs for the other builds just before they expire. It seems that GitHub will expire our logs after 3 months. So today is a good time to capture what exactly happened in the other failures so that we remember it for posterity. These 2 failures, we couldn't figure out what's wrong because the logs have expired. So let's move on. Now, this is interesting. This failure here is, it's a compile error. So this is the second compile error we've seen, and the third compile error we've seen. These compile errors should no longer be happening anymore if our developers use our new method of building PRs in our own repo. Today, we have a new system that we just roll out. We are getting some good feedback. So we'll be able to build our own PRs in our own repo. The idea is that you clone this repo, click on Actions, and there's a manually built CI for CI test. Then just fill in our NuttX repo name, our branch, and so on, and run workflow. That's it. That's all it takes to build a PR in our own repo before we submit it to the Apache NuttX repo, which means that our PR will succeed the compile checks and we will not see like the 3 compile errors you saw earlier on. We have also introduced a new option that allows us to compile one single target or one single def config in NuttX. All we need to do, again, is supply our NuttX repo, our branch. Then notice that there is a board config here. This is where we specify the def config. So if you want to compile only sim:/NSH, put it there. This is a helpful tool. I'm hoping that most developers will use this so that we can avoid errors like this. These errors like these are quite frustrating. Our developer needs to waste time to wait for these errors to appear, and also they are wasting our GitHub runners. We are charged by the GitHub runners that are consumed by these compile errors. Therefore, we really hope that our developers will all use this method here to build the CIs locally so that we conserve our GitHub runners and we won't have this peak happening again. Let us go on. Now, as we go on, we see it appears to be another compile failure. So it says that the data region overflowed. So the flash has overflowed. So this is a linking error. It's likely caused by one of our builds becoming too big. This thing could have been prevented by doing a manual build in our own PRs, in our own repos. So that's altogether 4 problems that could have been fixed if we built locally in our own repo before we submit the PR. Moving on, we see another download failure here. This download failure is for the libcxx, libc++. Again, we believe this will be fixed once we do the retry of CI builds. The retry will also re-download this library, and hopefully within the retry, it will work. Another failure here, this time, is for the Nimble download. Nimble is a Bluetooth library that came from our sister project, Apache Minute. This Bluetooth library failed to download. Again, with our retry of NuttX CI builds, we should be able to fix this. It should just retry and re-download the Nimble library, and it should succeed. Again, we are waiting for the testing to complete. It's very difficult to reproduce the download failure. It seems to be happening more often during peak periods. Right now, it's not quite a peak period, so we have to wait and see what happens. Another download failure here. Okay, we're not sure exactly what happened here. It's an ESP32 error. It says missing separator. It could have been a download error for ESP2 runtime that failed, or maybe it's a compile error, but quite unlikely that this is a compile error. So I would think that this could be highly likely a ESP32 runtime download failure. And if this is indeed a download failure, our retry mechanism should fix this. Now we come to 2 interesting failures that are highlighted in purple. Let's go and see what happened here. NTFC download failure. Fortunately, we have the logs to see what happened. Let's go in there. The job that's failing is in ARM12. We see ARM12 failing at a step for the install NTFC. So NTFC is a new framework that we roll out in January this year. It will do the CI test. Remember the part that runs a QEMU inside GitHub Actions to validate whether our NuttX code is running correctly within the QEMU emulator? Well, NTFC is the new framework that does that CI test. It's automated testing framework based on QEMU. This is new. Since January onwards, it will install the NTFC framework before it runs any CI tests. The problem with this installation step here is that it could fail. For some reason, it's downloading external dependencies. This seems to be doing a APT update or upgrade. And this could fail. So for example, we see that the download failed here. And again, the download failed here. So this download is coming from Ubuntu. It's doing an APT update and it's failing. Because of these failures, the NTFC installation step failed. And as a result, the entire job failed. Now, this is not good. It means that we wasted 1.6 hours of our developer's time. Our developer had to wait 1.6 hours only to discover that this job failed through no fault of the developer. It's through the fault of an NTFC download failure. What can we do about it? We have to implement retries or NTFC downloads. If an NTFC download failed, we have to retry. But what about the retry mechanism we spoke about? Unfortunately, this retry mechanism only works when the build starts and we are compiling a specific target. So like sim:/NSH. If sim:/NSH fails due to a failed download, it will retry, yes. But we are at this step here where we have not started any builds. Notice that build is the next step that is cancelled because our NTFC framework failed. So therefore, it's very, very important that we need to fix this issue here. So here we see the APT update, which is triggering this update from Ubuntu, and it failed. And I believe Ubuntu is kind of unreliable for this kind of situation. So we really have to do a retry if it failed. Alternatively, I'm wondering, do we really need APT update? Can we just skip it altogether? This container that we're running in comes from GitHub. GitHub, we believe, should be doing some regular updates on the containers. So maybe this is not necessary. But other things could be prone to failure. We could have failed here. We could have failed at a clone, downloading a repo. Yeah, so this I don't think would have failed. But these things we have to put wrappers around them to make sure that they will not ever fail. APT update, the APT install, the git clone, and another git clone here. These are potential points of failure. We have to watch out for errors and we have to retry. Hopefully we can do the same mechanism that we're testing today. We are doing an exponential backoff. The first time it failed, we will wait up to 60 seconds. The second time we failed, we wait up to 120 seconds, then 240 seconds, and so on. Why these strange numbers? Well, if we try to re-download too soon, let's say we wait 1 second, download again, 1 second, download again, whoever's the target of our downloads, let's say we're downloading from Ubuntu or from github.com, they might block us because we are spamming them with too many download requests too quickly. It appears like spam to these servers. Therefore, we do what is known as an exponential backoff. 60 seconds, 120 seconds, 240 seconds, and so on. We multiply by 2. That's why it's called exponential. But there is also another situation, what I call the lockstep situation. These processes, these jobs are running in parallel. We could have 10 of these jobs running in parallel. If every single one of these 10 jobs will do a download after 6 seconds, followed by a download after 120 seconds, then it will appear to our download target, let's say to github.com or Ubuntu, that there will appear to be 10 simultaneous downloads happening every 60 seconds, then every 120 seconds, then every 240 seconds. Again, spamming. They will block us. Which is why we need to do a randomized exponential backoff. Instead of waiting strictly 60 seconds, we will wait between 1 to 60 seconds, and again later 1 to 120 seconds, and 1 to 240 seconds. If you look at the code for our testing of the CI build retry, under here, we can see the retry mechanism followed by the exponential backoff. We will initially set the backoff to 60 seconds. Then after that, we will multiply by 2 every time through the loop. And we do a randomized delay. We are doing this right now in bash script, so I'm hoping that we can do the same exponential backoff with randomness inside our NTFC download script. Moving on, we have yet another download failure. If we click into this link here, we see that ARM03 is having the same problem. It's doing an APT update as part of the NTFC installation, and it fails. Okay, this is interesting. So might not be the APT update. It may be installation. We noticed that there's trying to install the Python stuff. The Python stuff has got here. It's apparently installing some Python stuff, and it's trying to fetch the Python dependencies from Ubuntu. And we see that it failed. So there's an error here. It failed to download from Ubuntu, and another download here that failed. So there are download errors that cause the installation of Python in Ubuntu VM to fail, and therefore our installation of NTFC failed, and that caused our entire CI job to fail. How much time did we waste? If we go back to the spreadsheet, we wasted half an hour. Our poor developer waited half an hour only to discover that the job failed because of NTFC download failure. What are we going to do about all this? Well, I flagged these errors out in a comment. Under this PR for initial support for automation testing for NTFC, I have raised a comment here that we need to implement the retry with random exponential backoff. These are the two examples that we saw earlier on. This is yet another example that we found that has the failed downloads. So we've seen 3 instances of NTFC installation failing. There could be more once I start digging through the logs. Therefore, it's very important that we need to address this issue. We need to make sure that NTFC installation will never ever fail. If it fails, we need to retry up to 5 times, hopefully, and with exponential backoff with randomness. Because we do not wish our target server, Ubuntu or GitHub or whatever, to be thinking that we are spamming that server. Therefore, we need to implement this randomized exponential backoff to allow us to re-download successfully. Right, so this needs to be fixed for NTFC downloads. Now, moving on, are there any other failures here? No, that's it. So, in summary, what can we say about this most expensive PR? We see that there are a lot of download failures. We see download failures for DTC device tree, OpenAMP. We see downloads failing for microADB. And then we see a download failing for MCU boot. And followed by a download failure for libcxx, Nimble download. It's incredible. Every single download is failing. And it's a different download failing each time, which is quite amazing. I'm not sure why this is happening. This could be happening because maybe GitHub is under extreme load and it's causing these issues. And finally, we have some issues with ESP32, which we think is a download issue also. That's what we hope to address with this retry of our NetX CI build. Hopefully, when we retry the build, it will re-download successfully. However, our retry mechanism will not work for NTFC. These two cases that we've seen. NTFC will only be fixed if we go into the NTFC code, which is still quite new, because it was only implemented in January, and fix it by doing randomized exponential backoff. We try our downloading with randomized exponential backoff. Only then we can fix these problems, and we don't really wish to frustrate our developers to see too many NTFC download failures. Also, we do not wish to waste GitHub runners, because after failing with these NTFC download failures, the job is cancelled, and we waste the GitHub runners for this job. Even though it says here that the elapsed time is 1.6 hours and half an hour, we have a factor of about 7.4 because of our concurrency. Remember that we run CI jobs in parallel, so there are more than one jobs running. According to our experience, for a 1 hour job, it roughly corresponds to 7.4 hours of actual chargeable time that are charged to the NetX project. So if it's 0.5 hours, elapsed hours that we wasted on this job, it means that we multiply by 7.4. So it's like 3.6, 3.7. So we wasted effectively 3.6 chargeable hours of GitHub runners. This time was charged to the Apache NetX projects, 3.6 hours, and it contributes to this peak here. Yeah. It's also quite interesting to note that this peak appeared in January and February 2026, and NTFC was rolled out in January. It could be a coincidence. It could be connected. I'm not sure. We have to go into data and understand more why our rollout of NTFC coincided with this peak period here. But we definitely must fix the download failure, as I pointed out here. I've seen 2 errors alone in one single PR, plus one other PR that I've seen recently. We have completed our analysis of the most expensive PR. This is the PR that consumed the most amount of GitHub runners, the longest GitHub running jobs for the period of January and February. And thankfully, we were able to do this analysis before the logs are expired. So now we have a record, well, it's not a hard copy, but a video record of what happened during that period for this particular PR. What do we do next? We move on to the second most expensive PR. If we look at the earlier spreadsheet that we compiled earlier on, this was the most expensive PR that we've just seen. The second most expensive PR for that period, in January, is this one, 18135. So we go into 18135. Again, we are not assigning blame to anybody, any developer or anybody in NetX project. We are merely trying to understand what happened for this particular project, why it incurred so much runtime, and why did our poor developer have to wait so long for this PR to build. So this particular PR here, unfortunately, was close. It went through a lot of builds, many times, but ultimately it was close. So we can say that it's kind of unproductive. We wasted all this time on a developer as well as the GitHub runners, only to see that this PR was not merged. Kind of sad. But let's find out why it consumes so much time. This particular PR in total, by the way, if you are curious how we created this spreadsheet, I just simply use the earlier spreadsheet. We are the earlier spreadsheet for the most expensive PR. I just copy and paste this entire spreadsheet, and I did a filtering. So when we go to the filter for this pivot table, there is a PR number here. So I just simply filter by 18135. You can see that 18135 is selected. And that's how we created this pivot table. So if you're interested in analyzing any other PRs, just go into this spreadsheet, make a copy, and do the filtering. And you see this nice table that shows you all the build times. How much time was spent on this PR in total? If we scroll down to the bottom, we see that it consumed 73 elapsed hours, meaning that our poor developer waited 73 hours for the build to complete and to clear this entire PR through many, many builds. How many builds? Well, we took an estimate. One build will take at most 3.5 hours. So when we divide 73 by 3.5, we get 21, which means that our poor developer had to resubmit this build 21 times. But why? Is it because our developer had to resubmit the build due to compile errors, or due to download errors, or due to some other issue? Today we'll find out. How much time was charged to the NUTEX project in terms of GitHub runners? Well, here's the number here. We'll take this number, multiply by 7.4 here. 7.4 is our concurrency factor. Through our experience, we discovered that because our jobs are executing in parallel, we work out to around a 7.4 factor in average, which means that 73 hours of elapsed time, we will multiply by 7.4 to give us 543 chargeable hours. These are the hours that are charged to the Apache NUTEX project, and that will appear in this data here. And therefore, this number is huge. It's like half of 1,000 chargeable hours. And that's why it's the number 2 most expensive PR during that peak period. And today we are investigating why we took so much time on this PR. Let's go back to the top. Now we have done an initial analysis. Notice that we have done a color coding. Our color coding is orange, not yellow, because it's a compile error. Let me show you why. Let's go in there. Fortunately, we still have the logs. This is in January. Because the logs are expiring from December onwards, we can see that it's failing due to build errors, compile errors. So lots of compile errors, it failed. Okay. Then next step, I believe, is our developer will fix this compile errors, will push the commit into the same PR, but unfortunately it failed again. Why? We can see that it failed due to similar compile errors. And this happens again and again. I've gone through the logs. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and possibly more failures. This was due to a compiling error with BL602 EVB11. I mentioned earlier on that this target is known to be quite unreliable. We're not sure why it fails sometimes, but this will never ever happen again because we have permanently disabled this target. NUTEX will never ever build this flaky target anymore. So we shouldn't see this. But we wasted quite a lot of time on these build failures. We see at least 10 that are happening due to compile errors. These are all compile errors that I checked. And I haven't gone through the whole list, but I have a high hunch that they are also all compile errors. Interestingly, I haven't seen a single download error within the first 10 failures. What could we do about this? Fortunately, we have rolled out this new feature that allows us to build and test our PRs in our own repos. We hope that all developers will use this feature to build their PRs before submitting to NUTEX, which means that we will save all these jobs, right? And how much time did our developer waste waiting for these jobs. Let's add up. 1, 2, 3. We add up the elapsed time here. We see that just for these 10 failures alone, we have 5.4 elapsed hours. So the first 10 compile errors wasted 5.4 hours of our developer time. So maybe this could have been faster if we used this method to do a compilation in the own PR, in the own repo, so that we conserve time for our developers. They don't have to wait 5.4 hours to discover that 10 of their jobs failed due to compile errors. But also more importantly, how much time did we waste on our GitHub runners? If we add up these 10 jobs, remember that our GitHub runners are running in parallel. Our GitHub jobs run in parallel, so that's why we have a factor of 7.4. We take the elapsed time for our build, we multiply by 7.4 to give us the chargeable runner hours for our GitHub runners. We wasted 42 chargeable hours of our GitHub runners, which is going to be a huge chunk of this peak period here. Therefore, I really hope, please, all developers, we should all use this repo here to build and test PRs in our own repos before we submit them to NUTX. If we do that, then we should not see this compile errors. Now, during January and February, yes, I understand. We do not have this nice new way of compiling PRs. I understand that it was quite painful for our developers to test their own PRs. Therefore, I fully understand that they are using NUTX main repo as a way to build their own PRs. But now we have this fantastic new way of doing it. So let's all use it. Because otherwise we will keep wasting GitHub runners and we will have high utilization. And we might be blocked from NUTX CI if ASF infra team discovers that we are using too many GitHub runners. Well, we don't have to blame them because remember that GitHub runners are coming from a shared pool across all Apache projects. If we are using beyond 25 GitHub runners, it means that we are depriving some other Apache project, like Apache Minute, of their GitHub runners, which means that their developers will have to wait forever for their jobs to start, simply because their GitHub runners are not available because we are using their GitHub runners. Therefore, we have to stop ourselves from using too many GitHub runners. Our average should stay below 25. This is quite bad. We could have affected some other poor developer in some other Apache project. We should never do that again. Therefore, everybody, please build and test PRs in the own repository before we submit to NUTX repo. Then our builds will not fail like this, right? Our builds should successfully complete, and it will be also a lot simpler for our NUTX reviewers. NUTX reviewers will now be able to review a PR that has completed the build the very first time. We should be able to prove it with confidence. Again, today's exercise is not really a witch hunt. We are not going to blame any specific person in NUTX team, any developer, anybody else. But it was a good experience. We've gone through the exercise of looking at the two most expensive PRs, and we understand the reasons. The most expensive PR, unfortunately, failed due to a lot of download errors, which we are now addressing with our retry mechanism. But we still need to fix the NTFC downloads to completely erase these issues in future. The second most expensive PR we discovered was due to a lot of compile failures, which could have been fixed by our new system for building PRs in our own repos. So therefore, yes, we have lots of ideas for fixing our CI system. We are now testing a new way to retry our NUTX builds, which will fix our download dependency issue. If anything happens to our ESP32 downloads, FTT downloads, Micro ADB, OpenAMP, Nimble, and so on, the retry will fix this, hopefully. But we also need help from developers. Please, if you are a developer for NUTX, please build and test PRs in our own repo. So use this mechanism, clone this, fork this repo, and use this way to manually compile a NuttX, your NuttX PR against our own repo. It could have been the entire, we could use this for the entire list of targets in NuttX, which covers all the platforms, or we can do a specific one. We can do a specific target like SIM-NSH. Right, so this is very useful information. We have explored the two most expensive PRs. We understand much better what contributed to this peak. We see that retries are absolutely necessary, and we also see that building our PRs in our own repos before submitting to NuttX is also super important. To finish up, I'll just go through one interesting finding that I made today about our retry mechanism. So we said earlier on that we will detect retries. We will detect any failed builds and we will retry the build. We noticed that some builds actually don't do they don't return an error status. This particular build here, ESP32, MCU boot update agent, notice that it tries to do a clone of the ESP32 Wi-Fi runtime, but it failed. Okay, I'm not exactly sure what's happening here, but it says that retry schedule. So what exactly happened? When you say retry schedule, does it mean that it will use something that is cached? It will use something that's already existing, even though the downloading failed? The funny thing is that it didn't return an error status. If it returned an error status, it would have said build error attempt 2 and continue. But our own script is not able to identify an error, which means that this particular target is not returning an error. So this is a bit mystifying. It says that this download failed, but yet it was able to return successfully. And it says retry schedule. Retry schedule doesn't mean anything for a NuttX job like this, so it's a bit strange because we only run this one time and we don't ever run this job again. So I'm not sure exactly why retry schedule failed. So it's just a bit, it's an interesting observation. I'm not sure what's happening here. Normally when we see a failed download, it will return an error status to the script, and therefore my script will do a reattempt. It will say build attempt 2 and re-download same thing. But this one is a bit unique. I haven't seen one that says retry scheduled, and yet it returns successfully. So I hope there's no error here. I hope there's no bug in my script. But this is something interesting that we'll continue to observe. Why is it that some downloads do not return an error to the caller? And what does this retry schedule mean? Does it mean that it's using an older version of the downloads? And would that be a problem? Right. Yeah, so this concludes our discussion for today. We talked about the number 1 and number 2 most expensive PRs in NuttX during that peak period. We saw an issue with NTFC downloads that must be addressed, otherwise it will keep happening again. Also, we looked at some compile errors, and which could have been fixed by doing a manual test of a PR within our own repos before we resubmit. And we finished up by looking at this very strange download failure in ESP32. Download failed, it says retry scheduled, but yet it didn't return an error to the caller. So we are now testing our script for doing the build retry. Hopefully I will update you in a while. And hopefully our folks who are maintaining the NTFC download, please look into these issues. We really need to do retry with random exponential backoff. Otherwise, we might hit some issues with our GitHub runners again during peak periods. And also, it's really bad for our developers waiting hours for a build to complete, only to discover that an NTFC download failed, killing their job, which is very bad for our developers, right? I wouldn't wish this for anybody. That's it for today. I'll update you in the next video. All the links I presented are in the video description. Thank you so much.